So just an overall question. Everyone here is familiarized with GPUs? Everybody program GPUs? For what purpose? Graphics, coding, vision? How many people are looking for graphics? Vision. Yeah. Yeah. So that is the thing, you know. When GPUs had been invented 30 years ago, the original idea was just graphics acceleration. And in recent years, slowly, the GPUs start to become more general purpose. So sometimes we call general purpose GPUs, GPUs. And the gap between high-end GPUs in the desktop and supposedly low-end GPUs on the embedded world are narrowing every day. It's getting smaller and smaller. So the thing is, the GPU is taking an important hardware part of embedded world. Our previous experience shows that when you try to accelerate things in the embedded world with GPU, sometimes you gain 100, 200, even 800% more performance when you take advantage of the GPUs. And that is becoming clear every day. We had previous experiences with the 96 boards when we compared the high keys with the bubble guns. And the bubble guns have the latest imagination VR GPUs. So we have incredible amount of performance just taking better advantage of these GPUs. And then, at the same time, the GPU is one of the closest part of the embedded system. We know very well about the ARM architecture. We know very well about the memory hierarchy, everything. But we know usually very little about the GPUs that are inside our embedded. So we have this idea induced by John Hall about the idea of designing an open GPU. So we spent 1 year studying the problem. And the fact is, most of the open GPU initiatives are just part of it. They are not ready for useful applications. Usually they are in the academic side, and 100% of them are based on the x86 ISA instruction set. So we didn't find out any open GPU project targeting the ARM instruction set. And that's the problem, because the real problems relay in the embedded world, not in the desktop world. Because in the desktop world, you can buy any NVIDIA board and do whatever you need. So our real problem is to see how we can scale up open GPU applications on the embedded world. So that was the motivation of our project. So why we need this? So because the GPUs are an important piece of hardware on the embedded world. So it's present in the various ARM chipsets. And it's very interesting because when you see the performance of these chipsets in the embedded world, the performance can range from 30 gigaflops to the latest claim of NVIDIA that using the GPU, they just achieved 1 teraflop with the latest TX1 256 core GPU embedded. So the symbiosis between the GPU and the CPU is quite relevant. Unfortunately, most of the GPUs are under industrial secrecy, and they are highly patented. Most implementations on Open GPU are experimental, and none are functional. So in our goal here, we decided to do a functional Open GPU project, because we believe that could be even important and relevant for industry. And also because it's really cool. When we talk about graphics and vision, everybody became excited, right? Because we are engineers and we like technology. So that's part of the thing too. And that's how I convinced young engineers jump in this project. So in terms of objectives, that are the requirements that we set up in our project. Need to be functional. So the first requirement is, we doesn't want just to write FPGA functional blocks for academic research or educational. We want to have it functional. So we decide to have a bottom-up approach because, you know, OpenGL, it's a family of libraries. You have OpenGL 1.0, 2.0, 3.0, 4.0, 4.5. We have the embedded version, and then we have the general purpose GPU libraries like OpenCV, OpenCL. So it's a whole universe of versions. So we decide to start from the very basic, where across all versions we can have the same stuff. So we decide to focus on basic graphics processing. Also because we can avoid patents on this. Need to be integrable. So need to be hardware compatible with all, let's say, 96 boards, for example. Need to be expansible. So the idea behind here was, if we put more gates, we can have theoretically more performance. Also, eventually could be synthesizable, either in FPGAs or ASICs. And finally, available. That's why we have this idea of, in future, designing mezzanine boards for the 96 board program with FPGAs, where we can eventually port our OpenGPU in this program. So our approach was using a co-design. Because, you know, when you design specialized hardware, the driver is key. So it doesn't make sense designing an open GPU if it doesn't take a lot of care into the driver. And the driver needs to be open too. So our idea was taking a standard and robust implementation of OpenGL. So we had picked Mesa 3D. And we recompiled Mesa 3D for ARM. And then upon Mesa 3D and another open source implementation named Galleon, we start to understand how this hardware abstractions software layer could be smoothly translated to hardware. So in fact, more than designing an open GPU, we had designed a methodology to smoothly do the transition from software to hardware on a scalable way. So in the way how we did that, if anyone in this room, if you have a special need in terms of FPGA, you can take that OpenGL building block and implement yourself. So we use it here, co-design approaches. So just to remember, Mesa 3D is the OpenGL implementation. It's very complete, it's stable. Any OpenGL software that you can imagine using these days, like Blender or even MATLAB, you can use up on Mesa 3D. And then Galleon is the driver's abstractions framework for Mesa. So we had ported these two environments for our ARM target. And we take very strong care on what we call the soft pipe. That is the hardware-software interface. So that is our target board, the TerraSIC, because at this moment we don't have FPGA shields for the 96 board, but that's our plan. So we have this Cyclone 5 integrated with an ARM Cortex-A9. So we believe that in future, we will be able to have one 96 board and put the shield board with some FPGA on top of it. This board costs something like $275, almost $300. And also we have a concern of having a mezzanine board that should cost almost the same price of the board itself. So we are targeting to have a mezzanine board that should cost something like $70, $90. So here's the abstraction. We have the CPU, and up on the CPU, we had ported Mesa. Up on Mesa, we had ported Gallium. And then we have the OpenGPU driver inside Gallium. And then this OpenGPU driver communicates itself with our bunch of FPGA gates, sending triangles and coordinates. It do the rasterization, and it gives back to our driver the quad fragments. So that is what we call the data path. The data path. So that was also very interesting, and we want to document that very well, because it's not about the architecture itself, but it's about the methodology of transferring the software abstraction to a hardware abstraction. In fact, we have a very smooth gradient from the software level to the hardware level in 40 steps. Upon this, we wrote the state machine for that. So that is the rasterized control state machine. And then we validated that. And I will show you the results. So at this moment, we are trying to improve the implementation. We focused mainly on OpenGL. But I heard some people talk about shaders and things like that. So that is our next step, implementing high-level functional blocks, because we have also the idea not keeping the project focusing only on OpenGL, but we're looking also for general-purpose GPUs. So some people in my lab is talking also about doing a similar project, not only based on OpenGL, but also based on OpenCL. So the demonstration. I will turn the computer here. Input. Yeah. So we have this TerraSync board. We ported Mesa, we port Gallium. We are pretty sure that we can do everything on the latest. I was just discussing that. We can port everything for the latest 96 board. But also, we have here a number of FPGA gates. And here is an application running up on Mesa and up on Gallium, doing the rasterizer up on the FPGA. In fact, I have 4 buttons here, but my engineer forgot to document that to me very well. So something that is beauty in this project, pressing these buttons, we can, in real time, shift the driver from the software only to the software hardware simulator that is even slower, to the FPGA implementation, and to the ASIC implementation. The bad news, that is not too bad, is that at this moment, the FPGA implementation, it is slower than the ASIC implementation. But doesn't matter, because what was our focus at this moment is to have a smooth hardware to FPGA transition. We need to do some optimization. But performance was not our first goal at the first moment, because the methodology is very complicated. And we want to open this methodology to the community, because we believe that the community will find ways to enhance the performance. since we have the methodology well-defined. And since we have the methodology, later, we need to have also the platform. And we do believe that the 96 board, mezzanine, with some FPGA, will be the ideal platform to industry. So we will have everything all set to scale up it later. So I will come back to here. So licensing is under discussion, but we hope until the next Leonardo launch a website, and John is helping us with the discussion about the licensing. And we believe that we had achieved all goals in our project. It's open source. It's just a question of defining the licensing and making it available. The basic graphics processing is fully functional. So any OpenGL application in any driver from 1.0 to 4.5, you can run applications up on our FPGA. It is scalable, but we need more work on this. We have a roadmap. So we just set up a roadmap to have our FPGA implementation faster than the ASIC, but that takes some weeks. So my engineers told me that they need something like 4 weeks to have a functional version faster than the ASIC, and we are working on that. Is OpenGL compatible? Because it's a driver, you know, we are using Mesa driver. So anything that you compile in terms of software using Mesa, it will work here. And also it's synthesizable. At this moment, for FPGAs, but we're looking how to do that also for ASICs. We have a partnership with Cadence, so we are seeing how we can wrap these functional blocks as possible open IPs for a given CMOS process. The future perspective. We want to break down the project on graphics processing and general purpose processing. So probably, since it's all about software, we want to keep compatibility with OpenGL, but we want to break down the project on a different direction, saying that is also an open CV implementation. We just have the methodology, and we need more people to implement that. And if someone is interested in this audience, we can share the methodology and start implementing these functional blocks to OpenCV and CL. The problem is, these blocks are a little bit more complex when they are in the high level. So one implication in the mezzanine board, we will need more gates. So that needs some discussion about what are the functional blocks that should be targeted in the first step. But again, if we move to OpenCV or OpenCL, we want to guarantee that it's functional too. We want to pick a piece of hardware that we can guarantee that just pressing a button and changing the driver will have it functional. Because later we can do software or FPGA optimization to gain performance. So we have our roadmap. So at this moment, my engineers are working this bottleneck that is memory access hardware manager. That is the real thing that is hurting performance at this moment. So we hope that in 2 or 3 weeks, we will fix that, and at least we expect that FPGA performance will be the same of the ASIC. And then in our roadmap, we want to work then in the video coding modules, texture compression, 2D functions, 3D functions, shaders, and eventually in future having a full OpenGL implementation in hardware. But that is a community thing, we need to do that together. Because as we go step by step here, the human hour factor affects a lot. In here, I'm talking about a project where we engaged 2 engineers 10 hours a week for 1 year to reach this point. And also, as I mentioned, we are establishing a strategy to reach an OpenCL implementation functional. Maybe at Burgengale, instead of bringing a graphics demonstration, we can have some kind of OpenCL functional implementation working on. And that's it. Thank you. And I'm very open for questioning and discussion.
Firstly, congratulations. This is a lot of really interesting work, right? So,
Thank you.
I think this has the potential to be a real disruptor in many ways. I work for ARM, and I just wanted to test an opinion with you, right? It's like any company that's in the business of making a commercial GPU product and the family of software around it, they would be remiss to try and participate in a project like this. They would be reluctant to perhaps openly participate in a project like this, right?
Oh, yeah.
For legal reasons, right?
Yeah.
So I suppose that's the reason why a lot of the ingenuity that has happened for an open GPU seems to be relegated to academia, right? There are academics working on it.
Yeah.
My worry is that perhaps you might not be able to make a really beneficial jump in capability without involving people who have the inside knowledge in terms of the techniques used, right? So how would you solve that?
Well, I don't know. I am a graphics guy.
Okay.
And in the past 20 years, I had participated. There is a special conference named IEEE Graphics Hardware Conference. So 50% of our students either go to work to AMD or NVIDIA, And for some special reason, these architectures became super closed. But there is a paradox because the software interfaces are fully open. Kronos is taking care of it. And maybe because this industry is closed, that's why the technology doesn't ramp up. So I don't know how to answer this question, but we believe that there is a space where from the software we can go to the hardware without hurting these companies too, because...
No, I totally appreciate the co-design and co-development model you have. That's brilliant, right? Yeah. The reason I use the word disruptive is because I think if you carry on down this path and you actually stick to your roadmap, you will act as a forcing function for some of the commercial people to rethink their current worldview.
Another point, just before John talks, that's a fundamental idea that something that we can explore as industry. You have the CPU, then you have an amount of transistors to do GPU, and then you miss anything. In our core design approach, we can have a situation where the GPU transistors in the ASIC can create a synergy with the FPGA. So that's another way to envision that and not create, I don't want to create any conflict with the GPU industry. In fact, they are my partners. I have some partnership with NVIDIA and with AMD too, we just realized that that is a missing thing, especially in the ARM ecosystem, because ARM takes care of 90% of our embedded world, And until now, we have only 2 options, Imagination VR and Mali, and a little bit of NVIDIA.
So I first approached Professor Zufo on this. It was kind of an offhand comment, and it was based around the fact that most GPUs have some type of proprietary firmware that is very difficult to get a hold of and only available in binary form. And then when you look at the long-term maintenance of that software, where the Linux kernel is changing rapidly, and there are issues around security and things like that, The problem of having that binary blob inside of the system creates problems. In addition, with a lot of the issues around security these days and various agencies that only have 3 letters in their name, any type of binary blob creates a potential for a trapdoor or some other type of security risk. So having a completely open implementation where you could publish all of the source code if you wanted to, allows you to be able to maintain that for all of time. And that was one of the things. The other thing was that, of course, things change over time, and the ability to use new algorithms and things like that in an open system with this would allow you to have to make changes and utilize those new techniques. Plus the fact that the FPGA is completely changeable. And I saw that in one moment you might be using it as a graphics processor, the next moment you might be using it to do other types of work. So these were all reasons why I mentioned this project to the professor in the first place, and then he found some students who wanted to work on it. But on the other hand, I don't see this as a real competition with people who are expending a lot of engineering work on developing dedicated GPUs. I think that there's a place in the marketplace for both. And I anticipate that there will be people who create specialized GPUs that will generate better performance than this would ever be capable of. But for a lot of embedded systems, you don't need that level of performance. You just need some simple, 3D graphics type of performance, or a simpler type of thing, and this would be perfect. There might be some cases where this would actually outperform a general purpose GPU, but I think that would be relatively small, okay? So I think there's both places. And while I've got the microphone, I'll talk about the licensing a little bit. We're just discussing this. The intent of the project is to be completely open. However, we also recognize that some people may want to take and add certain things into the mix that they feel that they don't want to distribute the source code on. That's fine. I think we can come up with a model where, for the most part, the code is available through GPL. But if a manufacturer wants to come back to university and license it on a BSD or MIT license or Apache license, that they would be able to. The concept here is that there would be one body that would hold the copyright for all of the code, and they'd be able to license it any way that anybody wanted to. But for the most part, we want to be as open as possible to allow the community to be able to contribute to this. So it might be, generally speaking, a GPL license, but alternatively licensable under a open source license. And one last thing. We also want to start to put in protective patents. If there is any material here that would be patentable, to have a protective patent, but to pass on the patents to the Open Invention Network, so it would be freely licensable also. Thank you.
Yeah.
Talking about the FPGA implementation part of it, not so much the Mesa part, I would guess?
No, it wouldn't be Mesa, because Mesa is obviously open, but we haven't even started to look at the IP implications of this, okay? So we would look at the IP implications, and if there was anything, it's a protective patent. We don't want some idiot to go in and create some type of patent that would prevent everybody from using this technology. And unfortunately, in today's world, you have to do that. So, if there is anything that would be in that realm, we would put it in a protective patent, but make it freely usable.
Yeah, just a point, I'm an educator, so I try to consider my last year students as engineers. So the thing here is, if they fail the project, they need to spend another year, because in professional life, if we propose design anything and we fail, we are fired, right? So I came to this engineer and I told him, you need to be functional. So he was really worried about having a functional implementation. But it's not me, but he had this idea of the co-design, that is brilliant. And I'm very proud, because This guy had his diploma, and he was looking to work on a bank. And I saved him. I bring him back. I hope to bring him to the next Linaro in Berkengale. So he decided to work in this project. But maybe more important than FPGA itself, it is the methodology. Because it's not about having the FPGA substituting the, NVIDIA, Imagination VR, they have years, Mali, years of experience designing workflows and pipelines. And they are cool. But sometimes we need something more. So even from the research point of view, we do believe that we have a model here where we can have the existence of the CPU, the FPGA, and the GPU together. So what we are discussing with Dan now, what kind of applications where we can have everything there, the GPU, the CPU, and maybe we need a little bit extra, an additional performance. Then that eventually we can fix with the FPGA. So we want to see applications either in the graphics world or in the vision world where the coexistence of transistor processing, CPU kind of processing, GPU, and FPGA live together. No? Hope to show that to you guys on Berkengale in September.
Burlingame.
Oh, yeah. I'm sorry. English is not my first language. Should be very fancy for you guys.
Well, Burlingame isn't exactly English either.
I have one question. How open is the synthesizable tools you're using?
Oh, that's another problem. You are correct. They are not open. Yeah. But that, I'm pretty sure that it's part of our problems when we talk about the mezzanine board. What will be, we have this board. I'm offering here, if anyone want to reproduce what we did, please just buy the board, and we will be pretty happy to, because we are a small community, Probably there will 2 or 3 guys looking for that here. But yes, there is some licensing. But that's another part of the problem. How we will open the workflow to synthesize the FPGA only, because everything else in this pipeline, everything here is under the Linaro framework. So easily, and Wookie inspired me a little bit. So based on his last lectures at Linaro a year ago, I came to guys, we talk about Mesa, Gallium. In fact, I hope to show you guys in Berkengale running Blender up on it. So complex applications, We did that. We ported Blender to the Bubblegum. That is a high-performance GPU 96 board platform. So the problems regarding synthesizing became here, That's another thing that we should take care. That's why choosing carefully the FPGA for the mezzanine board is tricky, Because I will recommend trying to adopt an FPGA. There is no FPGA initiative that is fully open, but we can try to find one that is at least open enough to these community purposes. But you are correct. That's an excellent question. It's still open.
There are some initiatives in the open source world to create a FPGA toolchain, which will be completely open. And this is an example of an FPGA that is contacted through a USB 2. This is $21 in the United States and works well with the current state of the open FPGA initiative for toolchain. So I think that more and more when people start using FPGAs in different ways, there'll be more and more people working on these tools. The tools will get better and better. And again, it's not necessarily to create tools which will be better than the commercial tools, but just to be able to give people the ability to program these things and do innovation with them.